So today we will be discussing the birth of calculus. But first of all, what is infinity? Infinity is a concept that describes something that is larger than any natural numbers and has no limits. Calculus. Calculus is a branch of mathematics that deals with rates of change. Early sign of calculus was found in the ancient Egypt, Greece, China, and Middle East and India. So we will discussing ancient calculus. The first one is Egypt. The Egyptian already known the calculation of the volume and area, as you can see in the picture being shown on the screen. One goal of the integral calculus can be found in the Egyptian Moscow papyrus, but the formula are simple instruction with no indication as to how they were obtained. Now we have Greece. In Greece, Archimedes used the method of exhaustion, which is the mathematical technique for finding the area of a shape by inscribing polygons inside it to calculate the area under the parabola in his work Quadrature of Parabola, which is the exploration of ratio between area of a parabolic segment and the area of triangle like the image being shown on the screen. And now we have Eudoxius of Cnidus developed the method of exhaustion, an early approach to approximating area and volume that foreshadow limits. He used it to prove formulas for cone and pyramid volume like the image being shown, paving the way for Archimedes and the integral calculus. And we have the method of mechanical theorems during the Hellenistic period. Hellenistic period, sorry. Archimedes advanced the method of exhaustion with indivisible, a precursor to infinitesimal in the method of mechanical theorem, also known as the Archimedes method. The method reveals how Archimedes used the mechanical reasoning and geometric ideas to discover and prove mathematical theorems, particularly involving areas, volume, and center of gravity. He solved, he solved problems like finding the center of gravity of a solid in the area under a parabola. Next is China. The method of exhaustion was independently discovered in the 3rd century China by Yu Hu to find a circle's area, and in the 5th century, Zhu Jingxi used the method later called Calaveris principle, which is the volume two three-dimensional objects are equal if the area of their corresponding cross-section are equal at the every point along their height to find a sphere volume. And now we have the Middle East. In the Middle East, Al-Hasan or Hassan Ibn derived a formula for sum of fourth powers and used it to perform an early integration calculating the volume of paraboloid. And lastly, we have India. In India, Bhaskara the second explored the ideas resembling identical calculus, noting that the indifferential coefficient vanish at the extremum and recognizing that if x equals y, then sine y minus sine x is equal to y minus x times cos y, implying that cosine is derivative of sine. In the 4th century, Madhava, Madhava of Samagrama and the Kerala school applied the non-rigorous differentiation method to trigonometric Trigro trigonometric trigonometry, sorry, having hard time, function and develop infinite series of expansions. However, as Victor J. Kultz notes that they did not unify derivatives and integrals or establish calculus as a problem-solving tools which occur later in the 7th century Europe. So The next is calculus in the 1600s, which will be discussed by Clyde Malano.
Hey, good day guys. I'm Clyde Milanum and my report will be about calculus in the 1600s. This will be mainly focused on how Sir Isaac Newton and Sir Gottfried Wilhelm Leibniz both independently developed calculus. Now, a little introduction on Sir Isaac Newton. Sir Isaac Newton was an English polymath, active as a mathematician, physicist, astronomer, alchemist, theologian, and author who was described in his time as a natural philosopher. He was also a key figure in scientific revolution and the Enlightenment that followed. Sir Isaac Newton invented calculus in the 1600s while trying to understand the laws of motion and gravity through physics. Newton noticed that the math of the time couldn't explain the rate of change of things, like the speed of falling object or the orbit of the planets. Newton realized he needed a new mathematical system to describe this physical phenomena. He, he built on the work of other mathematicians, including René Descartes and Pierre de Fermat. He wanted to have a mathematical system to explain the rate of change. Then Newton invented fluxions and fluence, focused on the concept of motion and change. His development was motivated by physical problems, particularly in understanding motion, forces, and the behavior of celestial bodies. Now, what is fluxions? Newton introduced the idea of fluxion to represent the instantaneous rate of change. This is now what is the modern day derivative. And fluence, this represents quantities that change over time akin to what we now consider functions. Newton's methods were heavily applied to solving problems in physics, such as planetary motion, big sample, building on Kepler's laws and explaining them with his laws of motion and gravitation, developing the binomial theorem and extending it to fractional powers, a step towards power series expansions. Now, Newton also used geometry of motion. Newton often used geometric framework rather than the algebraic symbolism we use today. So, guys, that's his difference to Leibniz. Leibniz developed calculus on the bias of algebra, while Newton uh, has a bias on geometry. We will now move to Sir Gottfried Wilhelm Leibniz. Sir Gottfried Wilhelm Leibniz, or Leibniz, was a German polymath active as a mathematician, philosopher, scientist, and diplomat who is credited alongside Sir Isaac Newton with the invention of calculus in addition to many other branches of mathematics, such as binary arithmetic and statistics. Leibniz developed calculus independently around the same time, but his approach was more formal and symbolic, making it more accessible and easier to generalize. His key contributions are notations. Leibniz introduced the modern notation of calculus, which remains in use today. Just like the dy and dx for derivatives, and the integral sign for integrals, inspired by the summation of areas under the curves. Leibniz explicitly recognized the relationship between differentiation and integration, which we now know as the fundamental theorem of calculus. A symbolic notation allowed for calculus to be applied to problems beyond physics, such as geometry and other areas of mathematics. And though they both independently invented calculus, when they published their papers, there was some dispute among the two. And this is what happened. Although Newton and Leibniz developed calculus independently, a dispute arose between them. Newton's work on fluxions predated Leibniz's publications, but Leibniz published his findings first in 1684. The controversy became politically charged, with English mathematicians siding with Newton and continental Europeans supporting Leibniz. Modern historians generally agree that both men discovered calculus independently and contributed uniquely to its development. So Isaac Newton and Gottfried Wilhelm Leibniz never engaged in direct personal attacks during the calculus controversy. Instead, their feud played out indirectly through letters, publications, and intermediaries. Here's a breakdown on Newton's attitude and statement toward Leibniz. Initially, Newton and Leibniz had a polite correspondence. In 1676, Newton wrote letters to Leibniz via Henry Oldenburg, Secretary of the Royal Society, where he hinted at his work on calculus but did not fully disclose his methods. Newton even included an anagram of a key statements about his fluxions to stake a claim to his discoveries without revealing details. Now, mm, as the controversy escalated, Newton became more critical of Leibniz. He believed that Leibniz has seen his unpublished work during earlier exchanges and used it to develop his own version of calculus. Although Newton rarely attacked Leibniz directly in public, he orchestrated efforts to discredit him. At the time, Newton has a greater influence than Leibniz. So it will uh, affect how the how the dispute between them follow. Now, Newton's role in the Royal Society report in 1712. The synergy of their approaches enabled calculus to evolve into a universal tool for science and engineering. Key developments stemming from their work include first, example number one, applications in physics. Newton's use of calculus in formulating his laws of motion and universal gravitation revolutionized physics. And second example, mathematical rigor. Leibniz focused on formalism and notation set set the stage for later mathematical rigor on calculus. These findings developed the mathematics further in the 19th century and influenced further, other great mathematicians like Cauchy, Weierstrass, and Riemann. Third example is foundation for analysis. Calculus is the cornerstone of mathematical analysis and underpins much of modern mathematics, physics, and engineering. Together, Newton and Leibniz transformed the study of continuous change into systematic and powerful mathematical discipline. And their legacy doesn't end there. They have further what there is contributions in calculus. Another example, they their work gave birth to the unified notation and concepts. Leibniz's notation became the standard, while Newton's ideas about motion and change influenced physics applications. The two traditions eventually merged, leading to the powerful field of analysis that underpins modern calculus. Also, the limits, continuity, and rigorous foundations. Later, mathematicians like Augustin Louis, Karl Weierstrass, and Bernard Riemann built on Newton and Leibniz's work, defining limits and continuity rigorously. This evolution helped establish calculus as a fundamental tool in mathematics, science, and engineering. Today, calculus is essential in physics, engineering, economics, biology, and other fields, thanks to the foundation laid by Newton and Leibniz. Their work opened doors for understanding and modeling complex dynamic systems. Newton and Leibniz's dual legacies continue to shape calculus, making it both a practical tool for analyzing physical phenomena and a theoretical field within pure mathematics. Their insights into differentiation and integration transform our ability to understand and solve problems involving change and accumulation, creating a framework that continues to drive innovation centuries later. And that's all, guys. That's my report on the calculus on 1600s. Thank you.
Calculus, the mathematical study of how things change. It includes differential calculus, rate of change using slope as a function, and integral calculus, determining quantities like areas and volumes under changing conditions. Two people responsible for calculus: Isaac Newton, the guy behind the laws of cartoons, the guy who hypothesized light is made up of particles called corpuscles, which allow us to see color when they enter our eyes, or just the Apple guy, and Gottfried Leibniz. Both Newton and Leibniz are independently responsible for the foundations of calculus that we see today. Now, did calculus start with them? Of course it didn't. Let's go back in time. Too far. Babylonia was an ancient Mesopotamian state comprising of modern Iraq, Syria, and Egypt. The capital city, Babylon, was about 60 miles from modern Baghdad. Babylonians offered an early intuition on the infinite process. They could determine the square root of a rational number to any number of decimal places. A contributing factor was their sexagesimal number system that allowed for a compact notation. Sexagesimal number system has a base 60. That means they represent all real numbers using 60 symbols. This is different from the base 10 or the decimal number system that we use today. the 10 symbols being the digits 0 through 9. Babylonian mathematics recorded their research and observations on clay tablets called cuneiforms. This is a famous cuneiform that shows that the diagonal of a square is root 2 times its side. They were also able to define other numbers with potentially infinite precision, like the length of a year or even represent the value of pi. Fast forward to 300 BC. Babylonian astronomers thought everything that happens in this world, from changes in the weather to rise and fall of tides, was associated with the motion of planets. So the Babylonians used geometry to study the motion of planets, specifically Jupiter, since their god Marduk was associated with Jupiter. Recording velocities at instantaneous times, they could determine how far the planet travels in an interval of time. This was similar to finding the area under a curve with the trapezoid rule, which forms the basis of integral calculus that we see today. Did they do everything? Of course not. Around the same time in ancient Greece were the prominent figures Eudoxus of Cnidus and Archimedes. They were able to prove areas of shapes through the method of exhaustion. For normal polygons, say an octagon, we split it up into a number of triangles and find the area of each triangle, then add it up to get the area of the polygon. Circles are a special case since they can't directly be split into triangles. Half a circle is just half a circle. So they inscribed a polygon and gradually increased the number of sides, so the area of the circle would approximately be equal to the area of the polygon. But the area of the circle would only be the same as the inscribed polygon with infinite sides. From this, we got the concept of limits, and it also incorporated the idea of the infinite process. On to the medieval era. India had their share of contributions too. In the 12th century, mathematician and astronomer Bhaskara II wrote the Siddhanta Shiromani, which contained texts in astronomy with proofs using calculus. He proved that at its highest point, the instantaneous speed of a planet is 0. Actually, I don't know what that means, but that's what it literally says in this paragraph of a news article in a language you don't care about. And this paragraph talks about how some English mathematicians called Newton and Leibniz are known for this discovery, even though Bhaskara said it a few centuries earlier. One of the greatest mathematicians and astronomers in the 14th century India, Madhava, linked the idea of infinite series with geometry and trigonometry. He was able to formulate infinite series expansions for sine, cosine, arctan, and even pi. So you see these expansions here, you know, the one that we call the power series expansions? But nope, they're actually called the Madhava series. This is the Madhava sine series, this is the Madhava cosine series, and this is the Madhava arctangent series. But if he did find this, then why didn't Madhava get the credit himself? We can't find his work. The only sources were the mathematicians who referenced him. Newton and Leibniz and other Western mathematicians were 300 years too late. The history of calculus and mathematics isn't straightforward. Different countries came up with their own methods around the same time. Using this knowledge, we attribute its flourishing as a promising field to the people who tied it all together. Newton was a physics buff. His calculus was defined out of necessity to lay the foundations of gravitation and the laws of motion. So it's no surprise that he thought of calculus in terms of motion and called his calculus the method of fluxions. A variable of interest was called a fluent, and its velocity was called a fluxion. While Newton thought of his calculus in terms of motion, Leibniz had a more mathematical interpretation. To him, calculus was more of sums of infinitesimal distances, the same meaning behind the notation we use today. And so most of the notation we use is actually from Leibniz. So who took the credit for calculus? Newton conceived his ideas in the 1660s, while Leibniz came to similar conclusions a decade later, but Leibniz published his findings nearly a decade before Newton. Well, initially it was Newton, but after their deaths, both were attributed the title inventors of calculus. Regardless, as we have seen, calculus wasn't invented overnight. It's a branch in mathematics that has multiple roots from thousands of years ago, and it continues to power newer fields like machine learning and AI. If not for all these people, some of us would be doing different things. Hope you guys like this little tangent from the hardcore math videos I've been dishing out lately. Subscribe for more content on data sciences, and I will see you in the next one.